So, welcome everyone. I'd like to welcome you to session 3 today of the High Performance Seismology Cyber Training Workshop. The session we're about to start is called SCEC Community Models Data Access Tutorial. Um, I'll start with an overview presentation about the SCEC community models, and then our SCEC software development staff, Mei Su, will present a demonstration and tutorial on the interactive web viewers that we have for several of the community models. So the focus of this session is really on how to access the data sets associated with the SCEC community models. The data comes in a variety of forms and formats and kind of distribution mechanisms. So this is an overview of the different ways to get access. Um, the development of the models is really led by these two researchers, Scott Marshall and Laurent Montesi, and they're the experts in to describe the process by which the models are developed. And we can allude to that, but we won't focus on that during our presentation today. So I'd like to get started by talking about basically an overview, by providing an overview of the collection of community models that SCEC has developed. So community model development, these are largely Earth structural models that describe a wide range of features for Southern California, the lithosphere and the asthenosphere. So we have an emphasis on Southern California. Some of the models are statewide. Within the SCEC community, there's a term called CXM. That's a collective term that basically refers to any of the models that have been developed. And the list includes community fault model, community velocity model, the stress model, community thermal model, geodetic model. This is a paleoseismic database, and this is geological framework model, and then some software called UCVM, which is Unified Community Velocity Model. So it's a term, that CXM term is complex and refers to a whole collection of different models. One of the kind of development concepts, however, is that there's a consistency in some sense between the models. So as a simple example would be a fault model and a velocity model. In some cases, you might have a velocity transition or change as you move across a fault structure. And the models are being developed so that they're in some sense consistency between them. So this is the called the umbrella term, and a list of the currently existing models. 3D fault representations in the fault. The geodetic model includes both GPS, or now called GNSS, and INSAR, information about velocity strain rates and deformation rates. Community paleoseismic data includes paleoseismic data, including dates that have been derived from Earth samples that have been collected. Rheology model can identify and assign a parameter such as viscosity on a particular point in the crust based on the rock type and the temperature at that point that the user is interested in. Community rheology model is built on top of two other models, a geological framework model, and a temperature model. And so it's basically you have a geological type and a temperature, and the rheology model can convert that into and provide a viscosity value of some sort. There's community stress model, both static stress and stressing rates, a thermal model, temperature versus depth, and velocity model. Um, there are a couple of Southern California models that have been developed by SCEC, but we often work with models that have been developed externally. And there's a package called UCVM that helps provide access to a large collection of velocity models. Okay. The scientific goal is to provide an internally consistent suite of models that can be used together to simulate a seismic phenomenon. So these are pictures of some of the activities. These are active faults in the community fault model. These are sedimentary basins that have been identified and are exist in the community velocity model. For this session, what we're focusing on is the wide variety of data sets and the access methods that are available to get to these models. So certainly making the data available helps the scientific review process. So to support that, we've developed web viewers for several of the community models. This helps people search and download data. In other cases, a model are registered as data sets on Zenodo, and you can retrieve the model data in zip files. We're not going to focus on the research used to develop the models or evaluate alternatives, but those are topics that are addressed through the SCEC research program. And so we invite you to attend and participate in the SCEC annual meeting where community model development is discussed. Okay, so as we go through this today, we're going to survey the models and the data sets, but for the tutorial and the demonstration section, we're going to focus on these, on basically the highlighted models: community fault model, the geological framework and the thermal model, and the velocity model. So those are tools that have existing web viewers, and we're going to show you how those work and some of the features of them. Sometimes the home page or the overview for the information that we're talking about is called the SCEC CXM research page. In these presentations, there are active links. So if I go to this, if I click on this link, so then it will take you to the research page. And this gives a reasonable introduction to the collection of models, provides a list about the leadership, software, and links off to detailed pages about each of the model. So after I do the overview, then May is going to demonstrate the interactive model viewers. Here are a couple of examples. So this is the geological framework viewer, where you can select points, identify the geological region, then the lithology type, and give it depth and get a model-based temperature for that point. And this is the community velocity model viewer and a cross section that's been generated by the web viewer. So we'll see more about this in the workshop session, later in this workshop session. So let me start with the community fault model. So this is a homepage that outlines provides an overview of the community fault model. It's an active research area. The there's been a recent release of version 6 of the model. So the model is looking at what or looking for and trying to identify 3D representations of active faults in Southern California. Now up to 820 fault objects. And by active, the definition is evidence that they've moved in the last 10,000 years. This has been developed and refined over multiple kind of iterations, and each each release has a scientific review process. There's not only a preferred model, but also alternatives are represented within the current CFM6. So some of the key information and data sets associated with this and that are used by different research groups are the 3D geometry for the faults. So these are provided in an important data access or data product from the CFM. And if you just want to work with the fault geometries, they're in something called a T-surf format, triangulated surface. They're provided in multiple resolutions, including some that are quite detailed, and in different file formats, shape files or plain text or Google Earth KML. So to make it official, they've posted this on Zenodo. Now there's a DOI, digital object identifier, associated with it. This is the DOI for version 6. So if we click that link, it'll take us to the Zenodo page, and we can gather information about the model. There's information about number of downloads. So it's been only up there since April, but already has several hundred downloads. Description of what is in the collection, references, and then this is a 63 megabyte zip file that you download, and it provides the geometry files and other information. So that's one of the distribution methods. So we also have a web viewer that is available for the CFM. This is going to demonstrate this in a minute here, or in a few minutes when I'm finished the overview. This now delivers the fault model to a wider community, but a preliminary version of this was used for the scientific review process. So it actually really helps the science group because of the kind of the visualization and interactive access to this model data. The web viewer helps the review process. So just again demonstrating, you'll click on this and it'll take you to the model viewer, and May will show how that works here in a few minutes. Okay, so next significant and widely used model is the community velocity model. So the typical information that comes out of a SCEC velocity model is VPVS and density. So the researcher provides a point in the earth, lat, long, and depth, and then the model will return the VPVS and density for that point. From a model like this, you can you can calculate some sense derived quantities, VS30, Z1.0, which is depth to VS1, 1,000 kilometers or 1,000 meters per second, Z2.5, which is 2,500 meters per second. Quantities such as attenuation, QP and QS, are often calculated from these from the information that you get out of a velocity model. and these are used in, for example, wave propagation simulations. So the community velocity model has been a long-term activity within SCEC. It was, our initial one was called CVMS. Went through, got up to CVMS 4. It was last updated in 2003. A more recent model was developed at a group of SCEC collaborators at Harvard. That one's called CVMH for CVM Harvard. That was updated in 2015. If you go to the SCEC CVM research page, it will give you an overview of the community model activities, who's involved, and some of their activities, how the model development is planned or progressing. The community model, the most recent one, the CVMH, one distribution mechanism for that is the IRIS Earth Model collaboration page. So IRIS, now SAGE, is has a collection of Earth models. Many of them are more global models or larger region than like the Southern California CVMH model, but we've put the CVMH into NetCDF format and contributed it to this Earth model collaboration. So if you go to this link, and you'll go to the SAGE Gauge page, and you can find information about CVMH 15. So, and download it in NetCDF. So, so that's an access method for that model. There's also a velocity model viewer page, or this is the velocity model software. So in our work, the SCEC research community likes to evaluate the alternative velocity models. So we provided or have developed a software tool called UCVM that's intended to provide access to a whole collection of velocity models. And so there's a web page that talks about this software, and it's open source software that you can download. And we make a distinction between the UCVM software, which is this software framework, and the models themselves, which are basically managed independently. When a new model is developed, we go through a process called registering it into UCVM, and then researchers can query that new model using this standard interface. So I don't know, mentioned that UCVM is open source software, but it's designed to run on Linux, and it's actually designed, it was originally designed to support high performance modelers, people doing creating large velocity meshes for 3D ground motion simulations. So it's built to run on supercomputers and to compile in a supercomputer environment, to build very large meshes that have billions of points. There's MPI methods that are included in here. So the UCVM software, it can be a complex and large distribution, but it's open source, and we have a variety of ways to work with UCVM, including a web viewer and some Docker containers. But if you're a ground motion modeler and you're going to use it to build large meshes, you'll probably need to install it from source code on a supercomputer. Okay, so these pictures here with those colored rectangles and polygons are show the coverage regions for different of the velocity models supported by UCVM or registered into UCVM. Shows that some of the models extend to Northern California, some are offshore models. There's some very small scale detailed models that have been registered in or inaccessible. So again, or this code is available on a GitHub repository, and the GitHub gives a description of the various ways to get access to use CVM, depending on your use. Okay, and then the model viewer, which will show us here in a few minutes, is online, and one of the things it does is present you a list of the available velocity models. Okay, so a few more left here. So next is the community geodetic model. This provides basically crustal time series and velocities from GPS and INSAR observations. Both of these, often these kind of raw data collection, need to go through some fairly detailed processing to remove or to make the conversion into useful crustal velocities. And so that's been done by the research group that develops the SCEC CGM. So there's a homepage that talks about the CGM research. So that's available here. Talks about the representatives and the people involved in it. The geodetic model has been registered on Zenodo and has a DOI associated with it. So here's a link to those, to that data set. This will describe the different, when you retrieve the geodetic model, the different types of information and files that are provided. And it looks like a 1.9 gigabyte zip file if you retrieve it from Zenodo. Next is the community rheology model. So as I mentioned earlier, the rheology model is built up on other components. So it's comprised of three main ingredients: a thermal model, a community thermal model, a 3D geological framework, and then relationships that are applicable to high strain rate zones, to low and high strain rate zones. The constitutive relationships differ between those. So so this is kind of how it has dependency on these other underlying models. But there are codes and scripts that implement these relationships. So if the community rheology model is being distributed on the Zenodo, it includes the three-dimensional definitions for the geological framework in various forms, MATLAB scripts that can compute ductile flow laws, and other information. So if you go to Zenodo, you can retrieve a zip file. It has the geological framework regions or volumes defined in various formats, and then the scripts for computing ductile flow. And it's about a 3 megabyte zip file that you get if you retrieve it that way. The underlying models in the rheology include the geological framework model. So this describes rock types, lithologies, using 6 different mineral types. And then if you apply temperature to these different mineral types, you can get a specific rock type, and then a viscosity, So these are the, this is the geologic framework is an essential element for the rheology model. This is, as I mentioned previously, so this GFM, you go to the CRM page to retrieve that. So that's the same Zenodo site. Also required to is the, for the rheology is the thermal model. So there's a research homepage for the thermal model. If you go there, you can, it identifies what they call heat flow regions, and describes the thermal model that's being used as well as alternatives, and provides some downloads for the thermal model, including scripts from the homepage and references. It's been posted as on the Zenodo website. So if you retrieve the SCEC thermal model from Zenodo, it's included in a 21 megabyte zip file, and there's a description here of what files are included. And then here, when May begins her material, she'll show that there's a GFM CTM web viewer. So this is a interactive web page that allows you to identify the geological zones, but then also to select a point and depth and query the geological framework model and thermal model and return information of interest about that point. So the type of information that you get back from this is a collection, and this is kind of the community models being internally consistent. So you query, use this page to query, it'll provide VPVS density from CVMH, GFM region from the GFM model, heat flow region from the CTM, and temperature from one of the CTM thermal models. Okay, so that's the collection of models that essentially are in use and have been particularly we have development for web viewers. There's a existing model called the community stress model that provides both static stress and stressing rates. There's a web viewers under development for this. And there's a research page related to this. And if you go to the research page, you can, there's a collection of stress models that are available for download. So this talks about accessing the community stress model. There's actually several alternatives, and they're all available on the research page for CSM. But there's activity to develop a CSM web viewer. So that's my overview of basically summary of the community models, and the how to access the kind of wide variety of data sets that are available. So we're going to shift gears here, but and now May's going to give us introduction and overview of the web viewers that we have. But I'll pause for a moment and see if there's comments or questions. So Fabio or Scott, if you're, I'm assuming no, I've heard from you, but if there are any comments, you'll let us know. So otherwise, I think May, we keep going. Can you share your screen? Yeah.
Yeah, let me share my screen. Let me share my screen. So, hi, let me start my PowerPoint. So everybody can see my screen?
Yes,
Hello.
looks good.
Okay,
Yep.
good. Okay, so I have actually sent out 3 links on chat line, chat, and also on the
Slack channel, maybe?
Slack channel. Yes.
Okay.
So there are links there that we will use later on to put on your browser to actually try the web browser, web viewer directly. So, okay, so let's start. Hello, my name is Maechling. I'm a programmer at SCEC. So today I'm going to actually show you 3 different kinds of SCEC web viewer. The first one will be CFM, and the second one is GFM, and third one is UCVM. And for each browser, for each viewer, we will watch 2 videos, one about overview of it, another one is example, and then we'll have some hands-on exercises. Okay, the first one is the CFM web viewer. Okay, so I will show you how to get it. We'll see the overview video, and then we'll talk about a simple example, and we'll see the video for that, and then we'll do some exercises. First, so the easiest to get to the correct CFM web viewer is to go through the official research CXM page, and then go find the CFM page. And in it, there's actually a button called Data Access Tool that will point you to the latest version. So far, this is actually our second release. The earlier release is CFM 5.3, and now we are 6.0. And so this would be the most up-to-date official one. Okay, so this is the overview, and I'm going to play the video.
SCEC CFM viewer is a map-based viewer for the SCEC CFM. There are a couple of different sets of data to select from. CFM 6.0 preferred, which is the latest version. The alternatives, the ruptures, and the CFM 5.3 set. There are different base maps that we can choose from. This one we can even zoom in to see streets. We can select to include seismicity, which I have preloaded to save some time. Left is a list of all the faults, and the right is a map of all the faults. If we click on a fault entry on the table or on the map directly, the fault information will appear at the bottom. We can download fault geometry and metadata with these links. We can select a specific set or everything. There are several ways to search for faults. We can search by keyword. Let's try Sierra Madre. Only the faults that match the keyword will show up. We can also search by lat long, area, zone, section, or name, and even by average strike or dip. Let's search by lat long, which is very useful to mark an area of interest. Click and drag to mark an area. All the faults that falls within will show up on the map and on the table. We can also plot the faults in 3D. Now the faults are in their 3D space, and we can choose to show them in wireframe or surface or both. For seismicity, for the trace, the coastline, and the bounding box, and even legends. We can change opacity or change color of the faults. To return to the original view, just click the map view. The direction marker, pink is to the east, green to the north. You can save image into a PNG file, and if you want to share the view, you can also save it to a clipboard and then pass along. There are more advanced features, but we'll have to stop here. Thank you.
Hi, as an example, so I have picked a earthquake from the USGS earthquake map. So we have this event. Its magnitude is 3.1 and it's within our coverage. And it happened actually 10 days ago. So let's try this.
Searching with a set of lat long on CFM viewer. We will use search by lat long. Put in the location 33028 minus 116.008 for longitude. A blue box appears on the map, and it is our region of interest. It looks like a fault is in it. Let's select it. It is Coyote Creek Fault. Its properties are here, and the option to download is here. Different resolution or to get everything. Let's see it in 3D. Let's change its color and opacity. Let's try it with wireframe and surface. And let's see how it looks. Also, seismicity. This looks good. We will take a snapshot and copy to clipboard. Now we can send a link to this view to our colleagues.
So this is a view I have saved. And this one in the clipboard, you actually is a link. And for that, you can send it, share it, or even just send it to someone who actually can run the same browser command to get to this point. So you'll be able to see same view on two browsers. And we're going to see if we can, let's see. So I would like to switch over to an exercise. And so this is a sort of the question. So I would like to have you try to download a GoCat teaser file for Santa Susana Fault and Northwest View. And the hint is that it's near Simi Valley. If you guys go into the chat line or Slack channel and start up the browser with the CFM viewer, then we can try that. Let me see. Me too. You should be on this view. Everybody's okay? You got this?
We're watching the
Oh.
Slack channel, May.
Oh,
No
so
no questions so far.
no questions so far. Oh, okay. Actually, I was on the wrong page. Okay, so this is the CFM webpage, the viewer. And so Simi Valley is around here. So let's go a little bit closer. Okay, Simi Valley. Okay, Simi Valley. So I'm going to do search by lat long, and I'm just going to mark it. And let's see what's here. Do we capture? Yeah. So we got Santa Susana and Northwest View. Okay. So this is our fault, this too. Okay. So this concludes the first exercise.
So may I, Phil, can I ask a question?
Yeah.
So if you do 3D plot, is it going to 3D plot just an individual fault, or will it 3D plot all of the selected, all of the ones that are
all the
in red.
selected. It is all the selected. For
Okay.
example, if I go like completely select all of them.
Okay.
And I'll go to native. It's not coming up.
I
Oh,
think it was
okay.
a lot of faults.
Oh, okay. Yeah, let me start over. Okay. Well, there's actually 12 of them. See, it's not coming. Okay, so let me just try 2, see if that'll come. Oh, it could be also, if everybody's trying it, it might be actually floating too low is high. Okay, so this is the 2 faults.
Okay, good. Yeah, shows.
And I think this is actually the second exercise, so I don't
Oh,
want to switch back and forth.
okay,
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 so we
thanks.
just continue on. Okay, so I think we're gonna try to do it with a wireframe. It's actually pretty neat. And then you could do a wireframe with the surface. So those dark spots are the actual points with value. And so in the native form, this is all the data they provide. So it's really fine. And we can change the color if we want. And we can change the opacity. So this is the point that I was, oh, it's not very obvious. Let me show it. It's actually very neat. Let's see, I make this a little bit solid. See, do you see that light line? So it actually intersects in the middle, and some of the data for the see that shiny blue light. So that's actually for me as a novice. This is interesting. Okay, and then we can turn
So
on.
may I agree with that? So as the software staff, that you're showing that scientific community seems to think it's possible that faults would pass through each other, which I think there are multiple cases in the CFM where they intersect and they pass through each other. That's
right.
I didn't
And
know
then
that was
yes.
allowed.
Yeah, and there are parts where you think that they are supposed to intersect like this. You think they will pass through, but there's actually a gap.
Okay.
See, this is space. Okay, so let's see. Oh, I wanted to say that after we find an image we like, we actually can save it and then copy it, and then you'll have your favorite picture from CFM. So actually, one thing that was I want to mention is that one of the tester of the initial CFM viewer he was actually hiking somewhere in the field, and then he saw something that was interesting, and then he wanted to know what is it. So he actually took out his iPhone, plugged the GPS location in, and he was able to say, "Oh, it's that thing." It's like explain to him, what sort of confirm what he suspect what it was. So this viewer actually could run on regular iPhone, but I don't know if you want to turn on the seismicity because it's going to be like blobs of dots. But then for this to see a little bit of couple of faults on your iPhone is actually pretty neat. Okay, so let me go back to my slide. Here. Okay, so that was test 1. And let's see. Oops. And we actually sort of did the test 2. Yes, I just want to mention that it was a blind fault and intersect in the middle section. Okay. So this was the image I captured earlier when I was doing the slide. Okay, so that concludes the CFM web viewer. Now we go on to the GFM.
Okay, so
Oh,
just checking with Fabio or Scott, anything in the Slack channel. So,
No, I think you're good. I think you're good to continue.
okay,
Okay,
Good.
great, thanks.
thank you.
Okay, so we will have the same format as before, is to show you how to get it, and an overview, and a usage example, and some hand-on exercises. Okay, so GFM is actually a prototype viewer, and so it needs more refinement and more scientist input. And so if you have any requests or feedback while playing around with it, or you think there improvement that's needed, we really appreciate you guys, drop us a line, at scec.org and let us know. It's better improvement idea is will make it more useful for everybody. Okay, for this training, we are actually hosting this because this is a prototype. It's hosted on the Amazon EC2 resource. And so this resource will go away after the training. And so if anybody wants to have access to this after the training, please contact us and then we'll set up something up. So this is the overview. Okay.
SCEC's GFM web viewer allows user to retrieve CTM and CRM information under a geological framework. Let's have a quick look around. From here, we can select different base maps. We have different types of model overlays. GFM 1.0, CTM, and CFM. At the bottom are two tables where the result will show up. One is for material property, and the other is for batch result. Here we can manually input lat, long, and Z value. There's a preset location. Let me click to search. A blue marker shows where it is on the map, and the result is at the bottom. Or we can turn on map-based selection. Let's place some blue markers on the map. When we are done, we can download them into a file by clicking on the download arrow. One very useful option is to upload the region of interest in a file instead of entering it one by one. We will show this function in the example section. We can also look at geological regions in 3D. Select couple regions. Click on the plot 3D. Now they are in 3D space. We can toggle wireframe, add CFM traces, toggle the coastline, and the boundary marks. We can also change the color and opacity. If we have an image we like, we can save a snapshot of it in PNG. Thank you.
So this is the example I would like to show you how to extract data in a batch mode. So entering, search point one by one or clicking on the map is sort of not reasonable, especially if I have an input of 1,000 and 1,000 of lat long. And so we have them.
Searching on GFM Viewer in batch mode. GFM Viewer has a file input mode. Input file should look like this. It can be space separated or comma separated. Do make sure Z has the right sign. Let's Let's select a file to upload. This will take a little bit of time because several data sets are being accessed at the same time. Okay, it's done. Here's the download link for the material property. And we can download the result locally.
So this is the sample of the download file. As you can see, there are all of these fields. It tells you location, the region, DTM, heat regions, and even the rock types. And this is actually a very, very long line. I just have to chop it up to fit. Okay, so now we come to the exercise. The first task is to select 1 point per GFM region and retrieve all the property to a local file. And then the point is to use the clicking map view. And actually, I want to show you guys the next task because I think it might be easier to do it at this. Oh, sorry. Okay. The second task is to create a 3D image of San Gabriel in orange and Great Valley in blue in wireframe mode with CFM trace. So let's show. Okay, so we'll go to GFM. Okay. So you should have this on your browser. Okay, so the first task was to get a point per GFM location. So I'll do this. I'll just click away. Wow, I think I'm not going to click. I think there are like 23 regions, and there are some that is sort of hard to click. Okay, this is all I'm going to do. Okay, and the next task is to plot it, the region plot. So I think we wanted San Gabriel and Great Valley. And I want a Great Valley, San Gabriel in orange and Great Valley in blue. And I'm going to do it with wireframe. And then I think I have traces. So the traces actually CFM traces. And while you're spinning and looking around, you might get a little bit dizzy. And you think you lost your view, you just show map view, so come back. But this is actually a secret button. See? Just put a surface there. Okay, so now that I have this view that I like, I'll just save the image. And that's it for this exercise. Let me see. Back to the slide. Okay. So this was my snapshot. Okay.
So
Anybody
yeah,
have
before,
questions?
yeah,
Yeah.
good. Very nice, May. I'll just, one comment you made that I'll add on to was there are two modes. There's elevation and depth mode.
Oh, right.
And when you give the, so if you're in depth mode, it's positive numbers below the Earth's surface. But if you're elevation mode, it's relative to sea level. So negative is below sea level and positive is above sea level. So I just want to you mentioned, make sure you get the parameter or when you're careful about that your Z value matches whether you're in elevation or depth mode. So,
Right.
yep. Okay.
Thank you for pointing that out, that every web browser is going to have that eye about it. Okay, so the next viewer we'll look at is UCVM web viewer. We'll have the same steps, access, overview, an example, and an exercise. Okay. UCVM web viewer is based on the SCEC UCVM. So it composed of many models under it. And so it's actually you can think of it as a single access point for multiple velocity model under SCEC UCVM. Okay, so this is also a prototype viewer, and we are also hosting it on a Amazon EC2 resource. And so it's only for this training session. And so if you want to have access after the training, please let us know and we'll set something up again. So this is the overview. Okay.
SCEC UCVM viewer is a map-based viewer for SCEC UCVM. On the right is the interactive map filled with leaflet. There are several base maps that we can choose from, even one with a city street. There are several overlays from other SCEC CXM projects. This one brings in the CFM faults. We have regions from GFM, also regions from CPM. On the left are the actions. In the gray box are the workflow steps. First is to select a model or a set of models. Second, need to decide to use depth or elevation mode. And the third is to select which option to do. You could query for material properties or create a depth profile of a lat long location, or plot a cross-section by drawing a line across a region, or plot a horizontal slice of a region. For the last three options, they could either be for VS, VP, or density. And for horizontal slice, it can also be for Poisson and VS30 values. Let's check out the drop-down option. In this instance, we have a total of 19 different velocity models. We also have a set of various combination of mixed models using UCVM's tiling function. For instance, this is embedding all CVMH basin models into CVMS 4.26 M01 using UCVM tiling. The end result is a single virtual velocity model. This section has simple description of all the velocity models included in this instance. This section describes Z mode. At the bottom are the two result tables. Let's try the options. Let's try the query. Let's pick a point in the valley. Let's point in a mountain. And let's pick a point in the ocean. The material property are shown here in the first table. We can download the property to our local machine and it will be in a CSV file format. There is a batch mode input for material property query. Let's load up a set of points. By default, the location are hidden on the map because of the file could be very large. And let's toggle the eye to see where those points are. Next, let's try to generate some vertical profiles. Again, one in the valley, in the mountain, and one out in the ocean. Now we get a set of downloadable data files. We have a PNG file, a downloadable metadata file, and two downloadable data files in different formats. Let's do a vertical cross sections. Use mouse to click and drag to draw a line. Remember to double click to end the drawing. Let's start the search. We left out the option to specify vertical and horizontal spacing because we are keeping a cap on points to query. Here, it is done. It has a binary data file, a metadata text file, and a PNG file. Last, let's do a cross-section. Again, using mouse, we can click and drag out a bounding box. Let's start the search. The spacing is intentionally left out again because we want to keep the response time reasonable. Now it is done. It has a binary data file, a metadata text file, and a PNG. Thank you.
Oops. Let's see.
SCEC UCVM viewer is a map-based viewer for SCEC.
Sorry. So these are the plots that I have collected from the overview video. So the right, oh, you're nice. Okay, so you're seeing, okay, so the right is the vertical, the slide, the cross cutting. And the one at the bottom are the horizontal slides. I think it's at 1,000 meters. And this one is one of the depth profile. I don't remember which one it is, but it's one of the start. And the material property for the point, the single points are here. Okay, so let's go to the next one. Okay, so as an example, the question is, how do we plot something under a location like USC? So we would like to see what's a basin look like under USC. And so this is a video.
How to make a vertical cross section on UCVM web viewer. Let's make one near USC. First, select a model from the drop-down. Let's use CVMH LA Basin because it covers USC. And select 2D vertical cross section. Pick the starting point with a mouse click, drag it across, and click again for the endpoint, and click again to end the selection of the cross section. This is our cut line. Let's start the search. We will let it run a little bit. Notice the exact lat long is filled in on the left, and the depth is from 0 to 5,000 meters, and using the data type of VS. For this instance of web viewer, it includes 19 different individual velocity models, in addition to the background 1D model. Okay, I see our slice is done. We can download the metadata used for creating the slides. We can also retrieve the data points generated. We can also view the plots on the screen. This is a basin, and the dark red parts are no data.
Okay. So this is actually the image we were able to create from that cut across the basin. Okay. So as an exercise, so I would like to see if you guys can pick a point of interest on the map and find 3 different models that covers that point and actually draw a vertical depth profile for each model. So let's try to do that. Oops. I think I lost my browser. Oh, okay. I'm sorry. I don't think I could do that. Okay. So, let's see. I could not show you. Are you guys going to be able to do it by yourself? Yes? No?
We'll watch the Slack channel and see if there's any questions where
Question,
people trying
any
it.
question?
So
Eh,
while we're doing that, can we go back to your picture of the LA basin?
yes.
You
Okay.
know,
Sorry.
although
go
this
back.
is software oriented, in some sense, it's a remarkable picture. When I've heard the seismologists talk about this, is the basin is, they define it as depth to crystalline rock. So this is suggesting that in LA, it's like sediments almost 4 kilometers deep, and you only get to crystalline rock. I mean, at those great depths, that seems really pretty deep. But I think that's fairly consistent with other velocity models that LA is a very deep sedimentary basin, and the basin is filled with earthquake faults. But I just want to point out there aren't a lot of places in California where you have basins this deep. I think Ventura is another one. But yeah, it's really quite a remarkably deep basin. Okay.
Okay, thank you. This concludes my part of presentation. Like I have mentioned earlier, UCVM Web Viewer and GFM Web Viewer are prototypes. If you have any suggestion or any request, please send it to us. It's greatly appreciated to move it along and then make it very useful for everyone. Thank you.
Very good, May. Thank you. Appreciate you preparing that. Yeah, very nice, very valuable tools. So we'll give a moment here for if any follow-up questions. This is we're nearing the conclusion here of our CXM community model data access, and we appreciate all of you participating, and be happy to have follow-up questions or to field follow-up questions anytime during this workshop and afterwards. And we encourage you and welcome you to use SCEC community models for your research. So I checked the May, there's one question in about putting multiple markers down.
That should.
Is there an
yes.
option that users might? Oh, there's
I
a
think
reply.
I think we got that resolved. We just you have to make sure to click on the magnifying glass after you pick your point right to query it, and then you can select additional points. So that was all.
And I also would like to answer about the scale for the fault site. If it's for the 3D plots, right, Billy? Oh, is he?
Yes, thank you. Yeah, they already answered my question. Thank you so much. I was trying to play around.
Well, I think she's asking about the
I've
fault
got-
size question too.
Yeah, the first question you have.
Sorry, I didn't get the last part. Just my internet some or something.
I think you posed two questions. The first question is about scale, and the second one is about the marker.
Yes.
So when you mention about scale, is that for the 3D?
Yes, yes. It was a sort of suggestion. Is that possible when you have the shape of the fold in the 3D thing? There is not a scale that gives you any information about the actual size of the fold that you are seeing. Oh, I didn't find it.
Yeah, so there's actually no scale and actually no, I think even the direction is a little bit hard to put in. So we've been looking at it, but this was based on a VTK package, and it's actually a really new package that they haven't put in the scale for me to add that option in. So we will be looking out for it, and hopefully someday we'll be able to add a scale to the 3D plots.
Yeah, absolutely. Thank you so much. Probably when it comes when you are going to download the image, once you have the perspective that you want to use, probably the algorithm that generates the image would add the scale. But it's just fantastic. Thank you so much.
Okay, very good. So again, we thank you for joining our CXM data access tutorial. We have a session starting at 3 on CyberShake data access, and we welcome you to join us then. So at this point, we're going to break for about 30 minutes. We'll reconvene 2:45 for technical setup, because the CyberShake data access uses a Docker container. If you want help getting that set up, we can join us at 2:45, and otherwise we'll begin our CyberShake data access tutorial at 3. So thanks again for joining.